All right. Let's see. Make sure everything is good here. All right, we're going to go ahead and get started. So today we will be working on a problem where we have our gas over here flowing through an insulated tube um, on the inside of the tube, and then on the outside we have liquid flowing down. And so real quick here, we are going to do a dimensional analysis to see our relationships. So as you can see here, I've written out the variables that we will be using for this equation, for this situation. So first here we have our Kc, which is our mass transfer coefficient. We have our V for velocity. We have our density, our viscosity here, our diffusivity coefficient, and our diameter. And so we're going to, since we're doing a dimensional analysis, we're going to define the dimensions here. So for mass transfer coefficient, it'll be in terms of meters per second. Velocity will also be in meters per second. Density is kilograms per meter cubed. Viscosity is kilograms per meter second. Diffusivity is meters squared per second, and diameter is meters. And so to go a little further to break this down, we're going to break this into a matrix so we can further break down our units here. We have kilograms, it's in terms of kilograms, meters, and seconds. And we have Kc, have our velocity, have our density, viscosity, diffusivity, DAV, and diameter. So for Kc here, we have in meters per second. So we can put 1, 1, and 0 because, -1. So there are no kilograms within the units for Kc. And then we have meters in the numerator and seconds in the denominator. So the power for that is -1. And then that's going to be the same for velocity, 1, -1. For density, we have kilograms of 1, meters to -3, and no seconds. For density, we have kilograms of 1, meters, -1, and -1 for seconds. And then we just have meters for our got ahead of myself. We have 0 for kilograms on the diffusivity coefficient, 2 for our meters here, and then -1. And then for this one, we have 0, 1, and 0. Now, this is a Pi-Buckingham method, or Buckingham Pi method, either way. But for this, we have an equation of I equals N minus R. And what this means is I is our number of core groups. That's our number of pi groups. You'll kind of see how that breaks out later, but the I is our number of pi groups, our core groups, minus our N, which is number of variables. I equals N minus R, which is our rank. For this situation, our rank will be 3 because we have 3 linearly independent columns and 3 linearly independent rows. And so we have I equals 6 minus 3, which we know is 3. So we have 3 pi groups. So we're going to break that out into pi 1, pi 2, and pi 3. So how we're going to define these? We're going to choose our core variables. So the first one we are going to choose is KC. We're going to choose KC because it's the only one that can only be found through experiments. Everything else here can kind of be known through different ways, but KC, you have to find that through experiments. So our first one's going to be KC, and because, I'm sorry, somebody's blowing up my phone here. Because, oh my goodness, because velocity has the same units, that is going to be the next one. And then our last one will be viscosity. And so then we're going to just multiply the rest of the variables in. So we have we have density, diffusivity, and diameter. All right. Density. And those will be in there to some factor we don't know. So we'll put that to the A factor, DAB to the B factor, and diameter to the C factor. We'll see how much, to what power they are in the equation. And it'll be the same for here. Now, because they have the same units, let's see, density, DAB, and diameter. Because they have the same units, they will be present in both of these equations to the same power. So it'll be A, B, and C. And then down here we'll have they'll be different. C, D, D comes after C. B, E, F. And so now we are going to find to what extent are they in these equations. So how are we going to do that? Let's see, how much space do I have? Okay, let's see if I can. I don't want to. I'm going to do it over here. I'm gonna move this over. All right. All right. So, what are the units? So we're gonna do the first one first. What are the units of KC? The units of KC are meters per second. Units of density is kilograms meters cube per meters cubed. Units of diffusivity is meters squared per second, and diameter is just meters. So down here we are gonna have since this is 4 kc, meters, we're gonna put it in terms of meters first. That's gonna be, make it into equations, it's gonna be 1 minus 3 A, let me see, A, B, C, minus 3A, because meters cubed is on the bottom, so the power is -3. So 1 minus 3A plus 2B plus C. Did I miss anything? Nope. All right. And then we're going to put it in terms of kilograms. It's going to be 0, plus A. So we're just going to get rid of that. A. And then there are no other kilograms within this. So A, oh, I forgot. That's all equal to 0. And then A here is just equal to 0. So up here, that'll just cancel out. And then in terms of seconds, we have -1 minus B equals 0. And so B will equal -1. Right. And we're going to drag that up here. And so that is going to bring us to 1 minus 2 plus C. And that's going to equal 0. And thus C is going to equal to 1. And so now we found the power to which each of these is in here. So we have let me see, let me change color. A, B, and C. So we are going to go ahead and plug that back into this equation here. Let me see if I can move this over. So for pi 1, it's equal to Kc times density is to the 0 power, so density is not present, times dAB to the -1 power, so dAB is on the bottom, times diameter to the 1 power, so it's right here. And then we can do the same for pi 2, since it's equal. So velocity is equal to the density isn't present, dAB times diameter. And then from there, real quick, these are going to be equal to this is our Sherwood's number. This relationship here is our Sherwood's number, or equation. And then this is going to be our Peckel number. All right, correction. Peclet number. I'm bad at pronouncing things. Peclet number. And I might even pronounce that wrong. Moving on. Pi 3 we need to find. And so what are the units of pi 3? We have our viscosity, which is kilograms per meter second. Have density, which is kilograms per meter cubed. AB is meters squared per second. Oh, oops. D, E, and then diameter is meters. F. All right. So doing the same thing again. Break it up first in meters. So it's going to be -1 minus 3D plus 2E plus F equals 0. And then it's going to kilograms. It's going to be 1 minus D equals 0. So D equals -1. And then seconds equals excuse me, seconds equals to -1. Wow, I blinked. -1 minus e. And then that's going to that one's going to equal to -1. Yeah. So we are going to plug those in up here. So we have 1, -1 minus 3 plus 2 minus 2, excuse me, minus 2 is equal to f. Oh, excuse me, plus f equals 0. And that's going to equal f equals 6. All right, correction. This d here is positive because kilograms is on the top. My mistake. So 3 is instead going to be a plus. And so this is going to instead be f is equal to 0. And we're going to plug those back in. Let's see, d equals 1, e equals -1, f equals 0. All right. And so pi 3 equals viscosity times d equals 1. So it's going to be up here. E equals -1. So dAB. And f equals 0. So f, our diameter is not present here. And this is going to be our Schmidt's number. Let's see. And so let me move this over. We're going to use our core groups, our dimensionless variables here, to create a relationship. Ooh. Go on over there. Move that over. All right. And so we're going to use that to create a relationship, create our Reynolds number. So Reynolds number is going to be pi 2 over pi 3 times the inverse of pi 1. So pi 1 to -1. And that's all going to equal out to V times D over viscosity. And so what this is going to come out equaling to is going to be our velocity times our diameter times our density all over viscosity. That's going to be our Reynolds number. And then, so now we're going to move on to a coding. A relationship that we are going to be using in this coding is our Schmidt's number is equal to A times Reynolds number to some power, let's see, times Schmidt's number to some power C. All right. So we are now in the coding section. So up here, I've already typed in our basics. We have our NumPy that we have imported. That'll just be used as our solver, or as our for using the functions. We have our plot leads down here. That'll be used for later when we make our plots. So first off, we're going to start by defining our numbers. So we have our Reynolds number. Ooh, that's stuff on my keyboard. Ooh, whoops. Got our Reynolds number, got our Schmidt's number, and then we have our Sherwood's number, right? And we'll go back into that. But for our Reynolds number, that is going to equal, let's see, we're going to do NP dots random dot uniform. Just pulling some random number here from, let's see, the low is going to equal 2,000 based off of what the book tells us is the bounds for Reynolds number. And so the low is going to be 2,000. The high is going to be 35,000. So 1, 2, 3. And we're going to be pulling 100 values. 100 values. And so 100 values. And then, let's see, make sure that works. Okay, we're cool. All right. And so for our Schmidt number, it's going to be NP dot random dot uniform. And for this one, our bounds are going to be from 0.06, 0.06 to 2.5. 2.5 are the bounds for that. And again, that's going to be 100 points. All right, cool. And then our Sherwood number, as we did earlier, I defined the relationship, how each variable relates to the Sherwood's number. And so I'm going to reference that function because I don't want to mess it up. So we had we had A. Sherwood's number is equal to A, and in this case it's going to be 0.023. And that's going to be times our Reynolds number. And our Reynolds number is going to be to the B power, as I put earlier, which in this case is going to be 0.83. And then that's going to be times our Schmidt's number, and that's going to be to the 0.4 power. And so yeah, we have defined our Sherwood's number, but we also want to pull some values. For our Sherwood's number, we want to pull NP dot random dot normal. We want to pull normally distributed values. And for that one, the lock is going to be SH, our Sherwood's number. And our scale is going to be, so we want it to be about a 10% distribution from our Sherwood number. So we're going to put, we want to have a standard deviation of 10%, excuse me. So it's going to be 0.1, Sherwood. I'm tripping. And yeah, I'm gonna run that uniform. Cool. And then from here, we're gonna be doing our linear regression and matrices. So I'm gonna switch over to back to my tablet and I'll further explain that. All right. We're back here over on the pad. We are going to do our um, linear regression here. Explain that over here on the pad so we can write it out. Earlier, I made a mistake. This is the equation that I have written out. This is incorrect. Um, um, the Sherwood's number and the Schmidt's number are reversed. This is how, well, this is how it should be. So this is the correct formula. Yeah. And so we're going to be doing a linear regression, right? And so in order to, so first step for that, we're going to take the natural log of the equation. So that's going to be natural ln of Schmidt's number is equal to ln of n of a plus b ln of Reynolds number plus c ln of Schmidt's number. And then from there, we're going to make another matrix. And so, matrix we're going to make here, I'm just going to align it with this equation. You have Schmidt's number, Sherwood's number, excuse me, Sherwood's number, however many that's going to be. We're going to add 4 rows of 1, 2, 3, 4, and this is just kind of going to act like a placeholder for A. And so, and then we're going to also have ln of Reynolds number. Drag that on down. And then we're going to have the natural log of Schmidt's number. We're going to all have that in the quantity. And then we're also going to have our unknowns. So our, oh, my pointer isn't on. Our A, B, or C are unknowns. All go into this matrix. So we're going to rewrite that out as ln equal to x And so what we are going to do next is we are going to multiply both sides by the transpose. So transpose of x. And what that'll do, it'll just make the linear regression easier to do. So let's see. We'll do xt here. Ooh, not z. Z. And then for this situation, we are going to put those together to make that easier to move around. And then we're going to move that on over. So it'll be, let's see, xt. That's equal to our unknowns. And this will be the relationship that we'll be using further in our coding. All right, so now we are going to start building our matrices as we've defined them earlier. I'll see if I can put the formulas back on the screen, but the formula, the first matrix that we define as X, going to put that under NP dot column stack, which just allows us to add each of the rows to the matrix. So the first one is going to be NP dot one's like, and that's going to be, if you remember, the first row of the matrix, the X matrix, was just ones, and so we're going to make it the same size as, you can choose any of the aforementioned, the variables that we did up here. They're all put out the same size. So this gives us a first row of all ones, and then the second row is going to be np dot log sc, and then the last row is going to be np dot log of the Reynolds number. See what I miss. Gave it too many arguments. Let me fool it by putting it all under one argument. There it is. And then our unknown we defined as u. We define it as u, and that is equal to our, what do we define it as? First we're going to do np dot linealg, and then it's the inverse, dot inverse, we'll put that there, and we defined it as the transposal of x. So it's going to be x dot t, and in order to multiply matrices on Python, you do an @ sign. So x dot t times x. And that is going to be times let's see, it was times it was times the transposal x dot t times our Sherwood's number. So log np dot log of our Sherwood's number. Okay. Let's see what we missed. Whoops. Look, I didn't even follow my own rules. I literally just said multiply it by add. There it is. And then we're going to call u. Check our values. So the values here pretty much match up with this one. And so Now we are going to move on to the minimize set of it. All right, we're gonna do our minimize section of it. So it's gonna be a sum square first. So we're gonna define. I'm gonna call it SSQ to be different. SSQ is gonna be a sum square. In terms of A, then we're going to type return and SSQ be equal to MP dot sum, and then from there we're going to type in it's going to be our Sherwood minus the first iteration of A, which will be 0, times our first variable of A, times using this equation up here, Reynolds number to the power of A1 times Schmidt to the power of A2. All right, did I miss anything? All right, and then from there we are going to minimize. So excuse me. I live in Scioto, and I think a bird just hit my window. That is unfortunate. I might leave that in there. Okay, this is not in view, but it's minimize. That's going to be our SSQ. And our guesses are going to be the values we're getting from the book. So 0.023. 0.83 and 0.4. All right, let's see if that works. Cool. Whoops. Okay, so it seems I forgot to import the minimize function. So let me go ahead and pull that. So it's going to be IP dots. All right, we're going to run that again. Oh, whoops. I believe I forgot to square my sum square. there it is. And so our values here are about pretty close. So it seems to got a little bit of drifting, but pretty close to the values we gave. All right, and so we're going to move on to graphing our values. All right, real quick here, I had to go up to the third box up here. Earlier I had the Sherwood number before the Reynolds number, and that created some problems later on as we got to our graph. So I went back up and changed those, and then everything else, each of the arrays now are switched now. So we're gonna go into making our plot. Let me see. Even it out. Cool. Making our plot. So we're gonna type in fig equals make subplots. And then we are going to add in our line. So fig dot add trace. And so for this one, we're gonna plot our scatter points, and so it's gonna be add trace go dot scatter plot 3D, and then we're gonna put in our values. So the first one is going to be the Schmidt numbers values. So it's going to be np dot lens space, and the bounds are, as we said earlier, is from 0.6 to 2.5, and we're going to call 25 of those values. Interesting. 25 of those values. The next one's going to be the Reynolds number. np dot lens space. Yeah. And that one's from 2,000 to 35,000. 25 of those. And then we're going to characterize our plot here. So it's going to be mode is equal to markers, and size, we're going to make the size 3 just to make them more visible. So markers marker dot underscore size is equal to 3. So we'll go ahead and run that, see if that worked. Let's see. All right, real quick, earlier I had made a mistake, and that had caused a problem in the graphs later on. So up here, where is it at? Right here. I had the bounds for our Schmidt number to equal 0.06 instead of 0.6, and so that was also what created the deviations that we saw later on in the numbers. That's why they were slightly more off than normal, and so yeah. All right, so it seems my computer had run out of storage, and thus it did not record anything I did. So all of this did not get recorded. So um, I'm going to run back through it. Um, yeah, I'm kind of salty about that, but I'll run back through it um, and show us how we got this graph. So up here we made our first plot, um, and this showed our scatter plots, right? And so now we are going to uh, create our mesh wiring. Uh, we're going to create a mesh plane that kind of works as a slope line for the 3D plot. So what we're going to do is um, that oop, I'm gonna do mesh grid np dot mesh grid. And inside that, we are going to have our np.linspace. So the one that I typed in earlier, we're gonna do our Schmidt and Reynolds number. Gonna put those in there. Linspace. And the bounds for that are 0.6 and 2.5, as we said earlier. I'm going to pull 25 values from that. And then we're going to have our Reynolds number. So np dot space. Okay. And it's going to be from 2000. Our bounds are 2000 to 35,000. Yeah, and then we're going to add our let me define these first as our Schmidt or grid and our Reynolds equals. Then we're going to define our Schmidt number, Sherwood number. Let's go grid. It's equal to np dot ex p with our first index of u. And then we're going to use this formula right here. It's going to be a similar formula times Reynolds to the second index of u. Times Schmidt to the third index of u. So all right, and then we're going to convert those into our lines. So I'm going to put in for I, J, and K. Put in, do zip, and we're going to put our, let's see, it's going to be our Reynolds number, because that is X. Our, this Schmidt number, and then our Sherwood number, which is going to be our Z. And then we're going to do add the lines in here. So fig dot add trace go dot scatter. All right, and that's going to be with our x is equal to I, our y is equal to I, j, and our z is equal to k. And then the mode, these are going to be lines, right? So the mode will be lines, and then we're going to change the color of the lines to black so that they can contrast. So we'll do line color equals black. Run that, make sure everything's all right. Let's see, got my comma. Forgot that, I forget what that's called. Oh, forgot to make these the grids. All right, so we have our first set of lines right there, and so we want a mesh and not just lines. So we're gonna do that. I'm gonna add the inverse of that in here so that they can cross perpendicularly. So we're going to inverse these, reverse them. Comma. I'm going to switch these as well. And then we should have a mesh here. All right, so here's our nice mesh graph. I'm going to make some more changes here. These aren't quite necessary, but just to clean it up a little bit. So we're going to do fig dot update layout equals to, we're going to change our two things. We're going to change the axis titles, and we're going to remove these because we don't want those showing, just don't have a purpose here. So we're going to do show legend equal to false, and then I'm gonna do scene equal to dict x axis underscore title equals our Reynolds number, our y axis title is going to equal our Schmidt number And our z-axis title is going to equal our Sherwood number. So update that. And there we go. There is our new and improved graph.